All right, guys. So what we've been talking about is SOHCAHTOA, right? Okay, so SOHCAHTOA is sine of something is equal to opposite over hypotenuse. Okay, cosine of something, an angle, is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent, right? And each one of these opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, those are ratios, obviously, right? Okay. So I'm going to work with just one of these three, but what I teach you and show you about just one of them is going to be consistent for all of them. Okay? So let's just deal with sine. If I say sine, and then in those parentheses, we're always going to be putting in an angle measurement. Okay? And it is a value, but it's going to be an angle measurement. And what gets spit back out then is a ratio. Okay? When we're using our calculator, obviously that ratio is always going to be expressed as a decimal. Okay? Now it might be terminated, it might not be, but that's what we get. Okay? The sine, cosine, tangent, the input is an angle, the output is a ratio. Does that make sense? And that output is something that we've been using as a scale factor. So if I get a ratio of like 0.5 back, that means that's a scale factor for how sides of the triangle, the sides of that one triangle relate to one another in regards to being opposite and hypotenuse. Does that make sense? Okay. So that's a nice thing. That allows me to find distances. So it allows to find distances. Okay. But there's a second part to this second component, and it's what we use to allow ourselves to find angle measurements. Okay. So we take this object, it's called sine inverse, and we write it that way. Okay. Sine inverse, that's the way we have to say, either inverse sine or sine inverse, either way, is how you have to verbalize this. Okay? I get a lot of people say opposite sine. Well, opposite means multiply by a -1. Okay? That's not what's going on here. So we need to know what verbiage to use so that we can communicate our ideas accurately. Because if I say opposite sine, then you're communicating a completely different operation. Does that make sense? A different procedure. So this is sine inverse. Now that -1 is a notation thing. It is not a exponent. Does that make sense? Okay, it's part of the name, and it's not an exponent. Whenever you see that as part of a name for something, it refers to the word inverse. Okay, but what's going to happen if we understand anything about inverses? Okay, so let's kind of talk about a picture here real quick. Did you guys talk about functions very much last year in Algebra 1? You did. You ever seen this notation? Okay. So this is a function. Okay. I'm going to talk about this as being a function. Okay. It's a machine. It does something, right? I'm going to take an input. What's that? It's an apple. Orange. An orange you eat. Huh? You've never been to an orchard? Apple orchard?
I have, but I've never seen one.
All right. So when I put the apple into this machine, food processor, a bunch of blades in here, okay, wood chipper, whatever, that's fine. What am I going to get out? I'm going to get applesauce out. My applesauce bowl, right? Okay. Now, is there a machine that exists Is there a machine that exists that when I run my applesauce through it, I get back out the apple that I started with? No. There is no machine that does that, right? Okay. However, mathematically speaking, there are machines that do that for numbers. Okay. You know a lot of them. You've seen a lot of them. Okay. Let's say this machine here is the expression 2x plus 3. And this machine here is the expression x minus 2 divided by 3. Okay? And instead of an apple that we run through there, let's put a number through there. Give me a number. 7. Okay? If I put 7 in there, what gets spit out? 17 is the first number that gets spit out. That's my applesauce, right? Run that through the second machine. What's 17 minus 2? What do we do here? Maybe my function's wrong. Hold on. 2x plus 3 equals y. Oh, that's okay. That should be an x. Sorry. I got these two numbers transposed. Let's start over. It's x minus 3 over 2. Sorry. I make mistakes. Please. At least I own up to them. All right, so put the 7 through. 2 times 7 is 14 plus 3, right? Now run that through this machine. What's 17 minus 3? 14 divided by 2? 7. Do you see how it's what I started with? I run through one machine, get something different, run that through the same machine, I get back to what I started with, right? That means that those two expressions are what we call inverses of one another. The second one undoes what the first one did. Does that make sense? Okay. We have the same idea here with sine inverse. Okay. The sine inverse, what you end up doing, what you put in here, is actually the ratio of two sides. Okay. In this case, because it's a sine, it'd be the opposite of the hypotenuse. If you put it as a ratio or you put it as a decimal, doesn't matter. And what is that going to spit back out? The same number as the angle. It's going to spit back the angle. Okay? Now, here's the idea. If I have, let me draw this picture again. So let's say that this is the sine function. Okay? That's my first machine. This is my sine inverse machine. Okay? The idea is take a number like 30 degrees. Okay? Put that in this machine. So it would look like sine of 30 degrees, right? What is that going to spit out to me? 0.5. That 0.5 now becomes the input here. So put sine inverse of 0.5. Now type that in your calculator. And what's it spit back out? 30 degrees. Spits back out what I started with, right? That means those two functions undo each other. Because they're inverse, because that relationship exists, we have the ability to say, okay, now that I know if somebody gives me 30 degrees as the angle, I know that the opposite side and the hypotenuse divide to give me 1/2, right? If somebody gives me the opposite side being compared to the hypotenuse as a 1-to-2 ratio or a 1/2 ratio, because of this procedure, this process here, we now know that there has to be a 30-degree angle incorporated in that picture. Does that make sense? So it's ultimately working backwards from what we've already done in the last couple of days. Last couple of days, we started with the angle, and that generated the ratio. Now, we're going to start with the ratio. We're going to start with understanding what the side lengths are and how they divide, and that will then link us back to an angle that ultimately provides that ratio. Okay? And that's what the sine inverse, cosine inverse, tangent inverse buttons do for us. I want to show you a couple other maybe visual approaches for this. But this here is going to allow you to find angle measurements. Okay, ultimately that's what we're looking for there when we use this function. Okay, Now, I could teach you, until last class, I teach my 4-year-old how to do this. I teach her, here are the two numbers you use, here's the button you push on the calculator, and you do the same thing over and over and over and over again. Same exact process on every question. But she's not going to understand why she does it that way and how it's all intertwined and working. And I think it's important for you to understand how we do it, why we do it, because of how the next courses develop themselves and how you're going to use this algebra in other courses. If you bypass all the logic that I'm going to try to show you here in a moment, you're going to struggle with trigonometric equations in the next couple courses because you have to be able to address the algebra this way, okay? If you understand it here, it's going to make it so much easier when you deal with other, maybe not trigonometric equations, but other types of equations that incorporate inverses. You've done a lot with inverses in the past, okay? What is the inverse of radical x? Here's the question. Maybe if I do, how do I think about what we said about inverses undoing something, right? Okay. So if this was, let's say my input is 3. If I put that in there, I get radical 3. So that's my input. How do I undo radical 3 to get back to just 3? Square it. If I square that, I get back to 3, right? So does that make square rooting and powers of 2 inverses to one another? Okay. If, I mean, you do it all the time. 2x plus 3 equals 12. First thing you would do would be what? Subtract 3, right? Subtract 3. That's because adding 3 and subtracting 3, positive 3, negative 3, you probably talked about them because of maybe your 5th grade vocabulary at that time as being opposites, right? They're actually inverse operations. We call positive 3 and negative 3 additive inverses. Okay, that's the math phrase for them, okay? Meaning that they get you back to a starting point, they get you back to 0. What's another word for multiplicative inverses?
Multiple inverse. Like dividing. And what is multiplication and dividing?
Well, what do you guys remember from algebra? Should talk about this like first, second week of Algebra 1. You start identifying additive inverses, we call things called multiplicative inverses. What those words referred to?
It's like 2x equals 12, and you divide 2.
Okay, so if I have 2x equals 12, I can divide by 2, or I can multiply by what? 1/2. Now, why does that give me the same result? Because 2 and 1/2 are what on us? Reciprocals. Reciprocals is a kind of a layman's term for what we call multiplicative inverses, okay? Meaning that multiplicative inverses get us back to what we call the multiplicative identity. If I take 2 reciprocals and multiply them together, what do you get?
1.
You get 1. That's the multiplicative identity, meaning that whatever I multiply by 1, I never change, right? Take 12, multiply by 1, what do you get? 12. Take pi, multiply by 1, what do you get? Pi, okay? So the multiplicative identity is the number that I multiply something by, and I don't change that something. The additive identity is what number? What's the additive identity? What number can I add to something and never change that something?
Yeah, 0.
0, okay? So additive inverses produce the additive identity. Multiplicative inverses produce the multiplicative identity. And these are things that maybe we should have talked about, but the reason I'm discussing them now is because we use them all the time, and they're addressing or using the concept of inverses that we're talking about right now, okay? And if we can understand that collective kind of group of things called inverses, it makes the work that we're about to do a little bit more simple, okay? If we were to take, so this is kind of where I'm trying to get this geared towards. If you were to take the cosine of some angle measurement, let's call that t, and I'll let t go between 0 and 90. We can determine those values, right? That's give me the cosine of those angles. Make sure I'm in degrees here. I am. So cosine of 35 degrees would give me 0.819, right? Okay. I can do the same thing with sine, and I get these numbers. Okay. So give me Give me a number. You say 17? Okay. So let's say that's the opposite. So if I'm talking about sine, let's say that in my picture, okay, so let's say if this is angle T here that we're interested, right angle here. If I'm using sine of T, 17 would have to have been the opposite side, right? Let's say that the hypotenuse has to be what compared to that? It doesn't have to be twice, because I don't know what T is. It's got to be greater than, right? Let's make it twice as big. Let's make it 34. If I go 17 over 34, okay, it gives me 0.5, right? If I were to take this slider and try to make this number here 0.5, should be able to do that. What's it tell me T had to be? Had to be 30, right? So the idea of what we're doing here is the sine inverse, cosine inverse, tangent inverse are going to allow that 30 to pop up on my calculator, okay? Because it knows that no matter what, if I have an opposite side divided by a hypotenuse and it divides out to be 0.5, because of similar triangles, it has to be attached to a 30-degree angle, okay? So it knows to spit back that 30. I'll explain maybe if we have time how that calculator is programmed to do that. Give me another. Let's do another example. Give me another number. 15. Let's go 15 here and 18. Okay. So now understand these two numbers are pretty close together, right? So when I do 15 divided by 18, 15 divided by 18, that number is pretty close to 1. Okay, 0.833. What that means then is that this angle here, these two things are almost the same length, right? So to make them almost the same length, okay, this side here has got to be really close to that side there, right? And if those two sides are really close to my picture, it's probably more something like this. So that's my right angle. And now this hypotenuse and this distance here are very, very similar to one another in size, making that angle pretty large, right? Okay, so let's see if that happens here, if I get a large angle for T. So I'm going to try to make that 0.5 go to 0.833, or as close. I can't get exactly 0.833. Close enough. Okay. So I get there 57. Okay. I was hoping maybe it would be, let's do this. Let's go 17 over 18. Okay. For 17 over 18, try to make that thing get close to 0.944. That's a little bit more drastic, right? That's a pretty big angle for a acute angle on a right triangle. So we know what that, now they're not exact, but that if I were to develop a ratio of 0.94 for dividing the opposite side and the hypotenuse, it is always going to be attached to an angle that's roughly 71 degrees. Okay? Does that make sense to everybody? So we're going to use that concept to help us here. Okay? So let's do this. Let me show you this example real quick. If I go sine inverse, so you guys know where the sine inverse key is on your calculator? Okay. If I go sine inverse of some number, sine of t, and hit enter, I want to see what I get. So what I want you guys to do on your day3s, day4s, or whatever you got in front of you, hit the sine inverse key. So you're going to go second sine. So it puts that -1 up there. Okay. Then I want you to push the sine key. Okay, so it looks something like I've got up there. It'll have sine -1, parentheses, sine, and then it should open a parenthesis, and I want you to plug a number in there between 0 and 90. I don't care what number, 0 to 90, any number you want to put in there. And then close off your two parentheses and hit enter. And what does it give you? It gives you just the number you typed in, right? Okay, that's because these things are inverses. Remember what we said in that picture I drew on the PowerPoint, is that if I take, oh, I deleted it. The idea was if this is the sine function, this is the sine inverse. Remember, if I put 30 in, it gave back 0.5, right? So 0.5 was then what I put in here. And what did that spit back? 30, correct? So the notation that you just used, what we call the sine inverse of sine of 30, if that 30 would have been the number that I chose, is the algebra of creating that procedure. Okay? So sine inverse of sine of 30 gives me back just that 30. Okay? If we were to, deal with square roots, okay? If I wanted to undo this and get that x out, what do I have to do to both sides? Yeah, whatever this side is here, I have to square both sides, right? Okay? Well, that's the same thing that is being expressed here. I want this sine of 30, I want this 30 out, okay? So in order to do that, I have to use the inverse operation, and this is the inverse function, and this is just the way we write it for sine, cosine, and tangent. This is the way we would write the inverse for square roots and powers of 2's, but the principle behind the process is the same, even though maybe I write them differently. Does that make sense, everybody? Okay. So when I do this, let's kind of look back at Desmond, because people then ask, well, maybe it's just a coincidence that this happened with the number that I chose, between 0 and 90. And I told you choose anything you want to. But if I choose, I create a slider here that I'm allowed to change that t value. So right now, this is saying sine inverse of sine of 21. And what's it spitting back? 21. Okay? If I change that to 63, putting 63 right here, and what's it spit back? 63. Okay? So no matter what, now you can see here that as I slide this, no matter where I stop, I'm just basically doing all those calculations kind of almost instantaneously, right? All the sine inverse of the sine of whatever is going to always spit back the whatever. That's key for understanding the algebra that we're about to do. Okay? Okay. So, we understand that hopefully, and we understand that our calculator is programmed in a manner in which when I type in a ratio with that function, it's going to spit back to us the angle that's paired with it. Okay? So what I want to do right now is I just want to find the measurement of angle N. Okay? So in the direction somehow they'll say find angle N. So this is very similar to what we've been doing. The first step is that they highlight somehow an angle for you to reference all your sides off of. Okay? Yesterday and the day before, when we were trying to find side length, they would give you angle N to be maybe 35 degrees or something like that, right? So it drew my attention there, and then I labeled everything off that 35 degrees. Here, they're going to ask me to find angle N. It still draws my attention there. So whatever angle my attention has been drawn to in the problem, I then label all of the sides based off of that angle. Okay? I'm still having people come to me during walkout time, which is fine, and they cannot decide what the opposite and adjacent sides are. Make sure that you're able to do that. If you can't do that consistently, then we're spinning our wheels here anyway. Okay? We need to be able to identify those. Now, obviously, the only ones that have numerical values on them are the opposite and hypotenuse, right? Which trig ratio uses opposite and hypotenuse? Sine. Okay? So I'm going to write sine. Now, what always goes in the parentheses for sine? N. Okay? So if you put x in you put your variable there, right? Or what you're looking for. In this case, we're looking for an angle, so that's why that goes there. An angle always goes in the parentheses. Be careful of using x, because that's being used in the picture as well. So, okay, so sine of n would equal, what would be the ratio that is equal to? No, because you're going to grab your calculator anyways. So right now at 15 or 20 is fine, right? You want to write 3/4, that's fine. But 15 or 20 is fine. Okay? So here, this is where the understanding of what I've just told you in the last 20 minutes is going to come into play. We're solving for what here? The angle. So I need that n to be pulled out of that, right? And I'm going to make an analogy here if I had an equation like this, something that we maybe understand real well, if I had that equation right there, is x3 in that bottom left equation? No, I can't just pull the x out and say it's equal to whatever's there, right? Okay, I have to do what to get that x out of the radical? Square it. I have to do the inverse, okay? So it's the same, that's why I said it's an analogy, it's the same process here. I can't just pull this n out for any arbitrary reason, okay? I have to have a logical argument of why that n can be pulled out, and here's the reason. If I were to inverse this side, okay, we just talked about in Desmos, we put a t here, right? And sine inverse of sine, what happens to those two things? They cancel each other out, okay? Cancel each other out. Now, there's a little bit more to that we'll talk about in trig, because it only cancels out for certain numbers. So if you put like sine inverse sine of like 120 in there, you're not going to get 120 back, okay? The numbers that you have to put in there have to be between negative 90 and positive 90, and that's okay because for us right now, because those are the only numbers we'll ever deal with in a right triangle, okay? But we get that in the fallout. Does that make sense? Now, that was an equation, correct? So in that bottom left, when I squared the left-hand side and got x, what do I have to do to the right-hand side? Square the right-hand side. It'll give me 9, right? So if I sine inverse the left-hand side, I took the inverse of this side. I've got to take the same inverse to this side. So that's going to give me sine inverse of 15 over 20. And that's what I then type into my calculator, make sure I'm in the right degree mode, hit enter, and I get my angle measurement. Okay? Now, here's my argument to you. You're going to find this out. People have already asked, say, why do we go through all that algebra? Why do we go through writing sine of n equals 15 over 20? If I'm just going to grab my calculator and just, instead of hitting sine, I'll hit sine inverse, and then type in the ratio 15 over 20. Would you agree with that? Okay? And you're going to see that pattern every single time. You can do that. But when you do that, you circumvent the algebraic work that it's going to be paramount that you understand next year and the following year. So I'm trying to get you to understand that prerequisite information now is going to be necessary for you to learn now so that next year it's easier. Because next year you don't know who you're going to have for Algebra 2. I don't know who's going to be the Algebra 2 teacher. It might be, it might not be. I don't know. Okay? So here's the thing. You might get an Algebra 2 teacher that you've never had before, and they know that this is a prerequisite that you should have learned in geometry. And if they're of that mindset, they may never ever address why we have to take the sine inverse of sine to do this. Does that make sense? When you get to college, and this is, I wish this would have been explained to me when I was in high school, because it wasn't. Okay? When you get to college, you're going to look at your courses, and I wish I would have done this a little bit more. I was very successful in college, but I wish I would have had this mindset because it would have made things so much easier. You're going to sit down and you're going to say, okay, this is the major I want to major in. This is the degree that I want to get. Okay, and you're going to create kind of a pathway of courses that you need to take and when you need to take them. And you might have like course D, okay, course D out there in the future. Maybe my 3rd or 4th year of college, I got to take this course. And courses A, B, and C are all prerequisites for it, meaning I cannot take D until I pass and show proficiency in those first 3 courses. Does that make sense? Okay. Maybe I go through and I pass course A with a C. Maybe I go pass course B with B. And maybe I get to course C and I pass it with, let's say, a D. All right? I passed them all right. Passed them. Okay? It's like showing up to the Little League game and losing but still getting a trophy. Okay? I passed them, but did I really learn everything I need to learn to be proficient in course D? No. No. Okay? So when I'm in course D and that professor is talking about stuff that was information inside of A, B, and C, and I wasn't proficient at it, is that professor going to take his time to go back and reteach me stuff that I failed to learn on my own to begin with? No. He's going to let you go. He's going to fly right past you. Okay? And it's going to be up to you whether you sink or swim. Okay? So I want you guys to understand that because it's so much better for you to see that now than to have that happen to you where you get passed by and then learn from that experience. Does that make sense? Okay? Would you rather watch somebody else burn their hand on a stove and say, That's probably something I shouldn't do. Instead of you burn your hand on the stove yourself and then saying, well, I shouldn't do that next time. Which one would be less painful for you? To learn from somebody else's mistakes, right? Okay?
Maybe if you do it at a younger age, then it won't be as bad as for adults if you put your whole hand on there.
All right, so that's the thing, guys. Because people today have been asking, like, why do you spend so much time talking about this process? Because, and I do this with all my stuff, because I know the situations that you're going to be in later on, and I don't want you to be in a situation where you haven't been informed enough about what's going on to where you are struggling because of that. Okay? So what we need to do on our calculator then is sine inverse of, what was it, 15 over 20? And it gives me that angle measurement there. Okay? So 48.59. Now, that's kind of a question. It's going to be one of your kind of basic questions that I give you on a test or quiz in this chapter. Yeah, I'll give you a question like that. So now here's the next thing. If I'm struggling with that, there should be a way for me to check to whether I'm doing things correctly. And that check is to figure out what angle X is using the same approach. Okay, now if I look for angle X, is this the opposite side anymore? What side is it? Adjacent. So now, adjacent hypotenuse are what? What trig ratio? Cosine. So I say cosine of angle X is equal to adjacent divided by hypotenuse, right? How do I undo that number? Tell me that I've done this thing, that I solved for X and